Before our group starts, let me introduce to our project introduction. This project was developed using Cisco Packet Tracer to design and simulate a functional computer network for the ITT 300 group assignment. The network consists of two local area networks, such as LAN A and LAN B, to connect by two routers, which each LAN contains one switch, 10 personal computers, and one DHP server. In addition, a DNS server and HTTP application server were configured to provide domain name resolutions and web hosting service. The project demonstrates an implementation of IP addressing, subnetting, routing, and network service while ensuring successful communication between devices across different lanes. Next, the objective of this project. This project are to design and simulate a functional computer network using Cisco Packet Tracer by connecting two local area networks to routers. We also aim to implement essential network services, including DHP for automatic IP address assignment, DNS for domain name resolution, and an HTTP server for web hosting. In addition, this project applies IP addressing, subnetting, and routing to ensure efficient communication between devices across different networks. Finally, we verify the overall network functionality through connectivity testing and packet tracer simulation to ensure all devices and service operate successfully. Okay, next I will explain the network topology used in our Cisco Packet Tracer project. Our network is designed using star topology, where all end devices are connected to a central switch within each local area network or LAN. This topology is widely used because it is easy to manage, reliable, and simplifies troubleshooting. As shown in the diagram, our network consists of two local area networks, which are LAN A and LAN B. Each LAN contains one router, one switch, 10 personal computers, and one DHP server. The switch acts as the central connection point, allowing all computers in the LAN to communicate efficiently. Meanwhile, the DHP server automatically assigns IP addresses to the computer, reducing the need for manual configuration. The two LANs are connected through router 0 and router 1, enabling communication between both networks. This allows users in LAN A and LAN B to exchange data and access shared resources. In addition, our network includes a DNS server and an application server. The DNS server translates domain name into IP addresses, making network access easier, while the application server provides shared service that can be accessed by users from both LANs. Overall, this star topology provides a structured, scalable, and efficient network design that supports reliable communication between all devices.
Okay, now, so for the advantages of using the star topology for our network design firstly, it provides us with an easy network management because every device connects to a central switch, which is the hub. It's simple to monitor, troubleshoot, and maintain the network from one central point. Secondly, we can get a reliable communication. If one cable or device fails, it only affects the single connection. The rest of the network keeps running normally, unlike a bus or ring topology where one failure can bring down the whole segment. And then the third is that by using star topology give us an efficient network services. Data can travel directly from the device to the center switch, then to its destination, which then keeps consistent performance and predictable. And then lastly, it is scalable. Adding a new device like another PC or a server is as simple as plugging it into an available port on the switch without disrupting any existing connections. Together, all of these advantages are exactly why our group choose a star topology.
So first of all, let's start by looking at our addressing table on the screen. So to connect our dual star topology, we configured two main gateways. Router 0 handles our LAN A gateway on interface gigabit Ethernet 0/0 using the IP address 128.10.0.1. So for the router 1, we connect our one link via 128.30.0.1. To secure an excellent mark according to our project rubric, we also integrate a critical automated service directly into the network. So we deployed DHCP server A at 128.10.0.2 to dynamically hand out configuration DNS server at 128.10.0.3 for name resolution, and application server at 128.10.0.4 on the opposite side. The HTTP server B is deployed at 128 at 12.20.0.2 to manage our second local area network. So for the end device, we divided them symmetrically into two segments, which is LAN A, which called VLAN 1, contains PCO through PC9 with the IPs sequentially distribute in the VLAN in the 128.10.0 range, symmetrically with LAN B, which is VLAN 2, which contains PC10 through PC19, which takes their IP allocation from the 128.20.0 range. So every single PC points directly to its respective default gateway to allow a successful communication outside its own network. So moving on to our next is our subnetting strategy. These slides will display the mathematical formulation behind our design. So our architecture requires the three distinct logical segments to function without overlapping LAN A, LAN B, and also our H1 link. So as you can see under column 1, the baseline addresses are set to 128.10.0.0/16 for LAN A, and also 128.20.0.0/16 for LAN B, and 128.30.0.0/30 for our interrouter 1 link. So in column 2, we look at the address space. For both LAN A and LAN B, we utilize a default class B/16 prefix length, which use the subnet mask 255.255.0.0 using the formula 2 power of 32 minus 16. This yields 65,536 total addresses, or 65,534 usable hosts space per network once the network. And broadcast limits are subtracted because they use their standard prefix lines. The bit borrowed remains at exactly 0. However, for one link, a massive network address space is unnecessary. For a direct link connection, only 2 routers. So therefore, we modified the prefix to a highly optimized /30 using the mask 255.255.255.252. This means we borrowed 14 bits from the host section, so the formula is 2 power of 32 minus 30, so leave us with 4 total addresses. Translating to exactly 2 usable host IPs means there is 0 address waste in our router-to-router connection. Final slide, we analyze exact logical boundaries for each subnet block. The baseline address block allocated per standard subnet in the setup is 2 power of 32 minus 16, which is 65,536 addresses. For subnet 1, which is the LAN A, the network addresses evaluates 128.10.0.0 by adding a wildcard value of 0.0.255.255. We establish our broadcast boundary at 128.10.255.255. So this leaves us our usable host range running continuously from 128.10.0.1 to 128.10.255.254. For the next is our subnet 2, which is the LAN B. The calculation mirrors the first network. So starting the network address at 128.20.0.0 and adding 0.255.255, which is the wildcard, we established the broadcast address is at 128.20.255.255. This sets is our valid host assignment range from 128.20.1 to 128.20.255.254. So finally is our subnet 3, which is the one link. Our calculation shift to reflect the specialized /30 mask. So starting at the network address is 128.30.0.0, we add a tight wildcard value of 0.0.0.3. This results in a precise broadcast address of 128.30.0.3.
PC to PC same subnet ping. The PC to PC ping within the same subnet demonstrated our local switching capabilities. To perform this in Packet Tracer, we clicked on a PC in LAN A, navigated to the desktop tab, opened the command prompt and typed the ping command, followed by the IP address of another PC on that exact same switch. For example, ping 128.10.0.11. After pressing enter, the successful replies verified that because both devices share the same network address space, traffic flows directly through our local switch without needing to be routed. PC to PC different subnet ping. Finally, the PC to PC ping across different subnets confirmed that our static routing is fully functional. To demonstrate this in the software, we stayed in the LAN A PC's command prompt, but this time pinged a PC located on the opposite network by typing something like ping 128.20.0.10. After pressing enter, this test proved that traffic was successful, leaving a PC in LAN A, hitting its default gateway, traveling across our configured router to router link, and successfully reaching a destination PC in an entirely different network segment. PC to default gateway ping. The PC to default gateway ping proved that our end devices can successfully reach the router. In Packet Tracer, using the same PC's command prompt, we typed ping followed by the router's local interface IP address, such as ping 128.10.0.1 and hit enter. This is a critical checkpoint because the gateway serves as the exit door out of the local network. Seeing those successful replies confirms that our switch to router connections and the router's local interface IP configurations are fully operational.
Okay, next I will demonstrate the one connection between router 0 and router 1. The one connection network use the subnet 128.30.0.0/30, where router 0 has the IP address 128.30.0.1 and router 1 has the IP address 128.30.0.2. From router 0 CLI, I execute the command ping 128.30.0.2. The results show 100% successful replies, while confirm that both routers can communicate successfully over the WAN link. This one connection is important because it allows traffic to be routed between LAN A and LAN B. Without this connection, devices in different LANs would not be able to communicate each others. Okay, next is I will demonstrate communication between the router and device in the local area network. Router 0 acts as default gateway for LAN with the IP address 128.20.0.1. To verify the router can communicate with devices in its LAN, I will ping one of the PCs. Ping 128.20.0.10. The ping is successful, which confirms that the router 0 can communicate with the devices in LAN A. This also verifies that the router interface is configured correctly and that the local network is functioning properly.
Okay, so for the ping domain part, first thing first, we must verify the PC's DNS server. So the first step is to open it on the PC, click PC and then go to the desktop, and then we click on the IP configuration, and then we check the DNS server field. And then second part is that after we've have analyzed and we have identified the PC's DNS server, we close the IP configuration and open the command prompt, and then on the command prompt we ping and put the domain name, like for example ITT300 December 2025.uitm.edu.my. And then for the last part, after that, after we ping it, if our DNS is working, we will get a reply from the domain, and then we'll get with the how many bytes and then the time, and that is all for the ping domain part.
So next is the HTTP server test and open website in the browser. So first is we need to click on the PC or the laptops inside our packet tracer topology that we want to test the connection from. Then a window for the device will pop up, and we need to click the desktop tab on the top. Then in the desktop tab, we need to look for the web browser icon, and we need to click on the web browser. And then we need to enter our server URL or our IP address. So based on our report, we are using the HTTP server, which is the http://128.10.0.4. So next we need to click on the go button to continue. So finally, in conclusion, this project successfully designed and implemented a functional enterprise network using Cisco Packet Tracer. The network consists of two LAN connected by two routers over a one link, with two switches, 20 PCs, two DHCP, and one DNS server, and also one HTTP application server. Through DHCP, devices automatically receive IP addresses, while DNS enable users to access the application server using a domain name. Network testing confirms successful connectivity between devices, communication across both LANs, and access to the web application, demonstrating that the network operates efficiently and meets all the assignments requirements for ITT 300. Thank you for your time, and that's all from us. Thank you.